Okay, fine. Okay, so my name is Stuart Haffenden. I represent Lancaster University in the UK. I'm part of the Highwire Doctoral Training Centre, whose Engineering and Physical Sciences Research Council project funded around the digital economy. So we're coming up with innovative ideas to promote things like Internet of Things and more importantly, sort of the social aspects of computer science and management and design. Today I'll be talking a bit about this concept called sonification and auditory displays, and I'll give you a bit of a background as to the motivation, as to why this is interesting, how it's relevant, what auditory displays are, how you use data as the processes of using data and mapping it to sounds to represent that information, the particular different techniques, specifically referencing specifically sonification and the aesthetics involved with choosing sounds that represent data, and then I'll give you a bit of an overview about the research I'm currently doing for my PhD and the impacts that we are able to achieve. So there is little doubt that we are a visually oriented society. Visual perception has evolved as a way of giving us means of efficiently navigating and interpreting our surrounding environment. As a result of this, a lot of the ways that we have designed our built environments and primarily the ways we codify and communicate information have largely remained visual in nature. Also, with the advent of obviously the digital age and the internet and all that, this has become a bit more important, and we see things like our televisions, computer screens, smartphones, even the signage on our streets, and more important, and even more recently, smartwatches, which has become a bit of a fad. So it's all screen-based technology. The dependence on the visual information has presented us with a number of key challenges, where the visual modality might not be the best way of representing information, or it might struggle to do this efficiently. Such examples of this include applications that require high levels of visual attention, such as driving a car, piloting an airplane, or even interpreting large data sets where immediate relationships might not be apparent by looking at streams of numbers, for example. Other implementations where real-time data streams are intended to be communicated to a user that are provided on a screen with limited screen real estate, such as smartwatches or activity trackers. There's a limit as to how much useful information can be presented on small screens. And more importantly, in a democratic context, obviously, access to visual information for people who have some form of visual impairment. So these are some of the areas where visual representations struggle a bit. So as a result of these strains, advancements in research and technology led us to experiment with different modes of interaction and information representation, such as haptic interfaces, which focus on touch, or auditory displays, which is a theme of this talk, that represent data through sound. So what are auditory displays? So auditory displays are interfaces that are primarily concerned with communicating information through the human auditory system. Auditory displays were developed to represent data or information by mapping it to sound parameters, by the process of filtering and scaling it to usable values, which are then mapped to parameters that generate or transform sound, with the purpose to highlight relationships between complex data sets. So the motivation to use auditory feedback to communicate data really lies in the ability of the human auditory system to understand far more complex and detailed changes in time than your eyes, and multi-dimensional information. So a good example of this is when you're listening to a piece of music, your ears have a very incredible ability to zero in on one element of the piece of music, such as a guitar, or listen to everything as a whole, and you're able to perceive lots of things at any time. So the human auditory system also counts with pattern recognition abilities that are not yet fully understood. So there's still a lot of exploration there, but we're not able to replicate them with any other means. They're also, as I said before, their auditory displays are designed to reduce the visual load And this allows auditory displays to also work in conjunction with visual interfaces. They're not mutually exclusive, which is something that is not been explored as of yet. We usually either focus one or on the other, and there's been very little scenario over them. So, auditory displays are made up of a number of different sonic components and techniques, and these are used to encode information in different forms. So the first one, which is more ubiquitous, are auditory icons, which are brief, distinctive sounds used to represent a specific event or convey a bit of information. Such an example would be dragging a file into your trash can on your computer and deleting it. You get that crumpling paper sound. That is an auditory icon. Secondly, we have sphere clones, which are essentially auditory icons that have very specific use, which are speech-based and are mostly used in interfaces for the visually impaired. One example of this is reading through a list of contact details on your mobile phone. Sphere clone of that, every time you pass a letter, you hear a little A, B, C, D, E, D. So it's a way of scrolling through information that you can't necessarily see accurately. Audification is a technique of mapping complex time series data directly to sound pressure levels. So this means when you grab vast amounts of information, plot them on a graph, and compress that through a digital means to generate a sound. So I'll give you a little example of that now. So it's important, I think, to hear things when we're talking about sound.
A lot of people ask me, what is data auditification? Or what's the multimedia artist doing working with NASA? I was approached by the solar and heliosphere research group at the University of Michigan with a challenge. Use audio to help us learn something new about the solar wind, which is what we call the stream of highly charged particles that's constantly flowing outward from the sun. You see, there are all these satellites out there constantly gathering observations, and we have more data than we know what to do with. We traditionally analyze this information through plots and graphs, which are essentially squiggly lines that we can read to determine speed and temperature and other various parameters. It's possible to translate these squiggly lines directly into audio files and play them back over speakers or headphones. Imagine that we cut this line into a groove on record. Through this process, 44,100 data samples get compressed into a single second of audio. When we listen closely to the frequency spectrum of the audio file, we found that sometimes we're able to hear things that were previously overlooked. Most solar wind turbulence sounds like wind hitting a microphone, which is not all that interesting. But sometimes the interactions between waves and particles sound like chirping birds. And occasionally we hear a whistling sound. Recently we pored over millions of data points and found something fascinating. You see, the sun released an explosive cloud of particles. And when we listened closely, we heard a unique whooshing sound. I passed the data to a scientist and they crunched the numbers. It turned out this feature is an ion cyclotron wavestorm unlike any that has been seen before. And we're finding that researchers can identify new features like these with very little training. From auditory observation to new scientific insight. That's how auditification works.
Okay, so that's one of the main techniques for auditory display, which is commonly used in applications that we've just seen with NASA, dealing with very complex data sets such as satellite data from the sun. The next technique, which is one I'll be focusing on and leads on to my area of expertise, is data sonification, which is the mapping of data for the manipulation of sound parameters. So this is a much more creative way, rather than just crunching some numbers and squishing down to a brief sort of audio file. It's more a way of generating sounds that sort of change and evolve through different ways of mapping. And it doesn't necessarily have to be in complex data sets such as the sun. You can do it with, for example, the weather, which I'll give you an example right now of how it sounds. So this. So yeah, this is a piece of music that I composed using weather data as input, and the idea was to see how we could use data as a compositional tool, and more as a way of showing people outside the scientific community how data can be used and how we can experience it in different ways rather than just graphs and statistics and numbers. So we have these sort of like parameter sounds that have usually carbon monoxide, carbon dioxide, methane gas, and stuff like that. So the presence of these sounds indicates and how often they appear indicates different levels of pollution in the air. You have a bell sound in the background, which is just basically a way to mark 1 hour that passes within the day. And we will slowly hear the light intensity from the sun come in and sort of bring in other pieces of music, which will also include sounds for temperature, which will trigger different notes and make it a bit more musical. So the temperature will be guided with a bit of melody. We'll get to that in a moment. You can hear the sun coming up now, but it's going from night to day. Okay, so that's just a brief example. So sonification is interesting because it gives us a way of connecting this data in a more sort of artistic way, and sonification has been largely used in those two aspects, either in an artistic sense, in installations and stuff like that, but also within more scientific things such as medical rehabilitation for people with mobility issues, where sounds can guide them to relearn movements that they were struggling to do. So it's a way of referencing biofeedback. So, the craft of composition is important in auditory display because psychoacoustic research has shown that people interact better with sounds that find pleasing. So a lot of the problem with the science of sonification research at the moment is that there's a top-down approach where designers of auditory displays assume that their display works, and then they just put it out there, and then people don't necessarily react to it properly, and they suffer from things called display fatigue, which is the hearing very repetitive and monotonous sounds, making it very dull. So the next sort of issue with that is that you can see here a discrepancy between how listeners interpret an auditory display and how they describe it using different words such as gas or solid, speech, and sound effects, front and back. And you here have what researchers would describe their auditory display like. So you can see here these discrepancies between how the designers develop their interfaces and how it is received by the people. So one of the next steps to improve that would be to do a user-centered approach where you work directly with the participants or who you are designing an interface for, which is sorely lacking in auditory display design. So my research project is focusing on how we can harness sound as a way of teaching people proper running technique using these wearable devices that are becoming incredibly fashionable and very useless, which because they get the majority of people who adopt these stop using them after 6 months. So there's a key question as to why that happens. And one of the issues is with this graph you can see here, you can see there is a sort of discrepancy in how the information is provided. A lot of it, representative feedback, refers to graphs and stuff like that. That's not real-time data, but data that you see after you run. So you see the graphs of your pace and how many calories you're burning and everything. And there's not much information that you can use in real time to improve your running whilst you're there. So the main problem right now is finding a way of providing assisted feedback in real time to runners. And some of the devices have started doing that, but they still are stuck to the screen-based technology, such as smartwatches, which are focusing on other parameters rather than just space, but also reducing biomechanic aspects such as ground contact time, how hard your feet are hitting the ground, for how long, and how much your body pops up and down. These are very weird things to represent on a very small screen on your watch, and when you're running, the last thing you want to do is keep checking your watch to see if you're, am I doing this right, and it's really hard to adapt. So my project is really looking at how we can design a wearable application using motion sensors that transmit this information to a phone that generates sound to create an assistive feedback for the person who's running, in turn sort of addressing these issues with auditory display design. So the outcomes of this research are really incorporating compositional techniques and aesthetic considerations into the designs of auditory displays and addressing these issues that I mentioned before, such as display fatigue and lack of user engagement with the technology. I'm also looking to provide a framework for user-centered design that addresses this issue that I mentioned of top-down auditory display design and get the people who are affected by the technology incorporated into the design process, and providing insights into the impact auditory displays can have on activity tracking and wearable interfaces, and finally exploring different use of biofeedback in an ever-growing consumer electronic market, which is one of the few areas that sort of this technology broken through to the main. So yeah, that's it for the questions.
Yeah, if you can maybe elaborate a bit more about kind of data exploration. So you talked about sonification and the previous one, which I don't remember the
Audification.
Yeah, then does you composing something which is pleasing, but then does the data scientist person who's now looking to explore the data?
Yes.
So how does this kind of
So yeah, there seems to be a compromise right now that between how faithful the data representation is. So whether sometimes you want to make it too pleasing, but then it becomes very ambiguous. Whereas if you make it very precise, you suffer from display fatigue. So that is one of the important things as to why user-centered design is a key to the process of designing it, and why we haven't seen a bit more of a clear answer, which I don't know yet either, as to how we achieve a compromise, a balance between those two things. That is why I'm looking to this idea of incorporating aesthetic considerations into a more scientific research aspect into the design of
kind of a case-by-case basis then.
Yes.
But I guess you can always have like a knob that the user can turn and then you go.
Yes, I mean, yeah.
Right? I mean, if he's really interested into the details, you hear the ugly sound. If you want to hear the nice thing, then you just turn off the.
Of course. Yeah, I mean, that would be an interesting workaround for sure, giving people the flexibility to choose or narrow in into things, eliminate data streams, bring them back in, which is why it's important that we ask the people, what are you interested in listening to? What are the sounds that motivate you? What are the sounds that, how do you interpret these sounds, which is sorely lacking. Yeah. Thank you very much.
Amazing.